Good evening, sir.
Good evening,
Good
sir.
evening, sir.
Good evening. Without wasting any time, we'll start with the discussion. So last class we have been discussing about spectrochemical series. Yes or no? So this is the last point of our discussion. So earlier we have seen valence bond theory and Werner's theory. Werner's theory just gives idea about the type of how many. Yes, Werner's theory just gives the type of primary valencies and what are primary valencies, what are secondary valencies. If a particular complex is added to excess AgNO3, how many moles of AgCl is obtained? So which chlorine is acting as a counter ion, which is acting as a coordinate bond, which is acting as a ligand, making a coordinate bond with the central atom. So like that, the discussion has been went on. So what is the concept you have studied in Werner's theory is just purely the type of primary valencies, secondary valencies, how many species are going to be formed, like what is the quantity of precipitate formed AgCl based on that number of moles of AgCl formed, how much chlorine is can be converted into the ionic form, all the discussion we have seen. Yes or no, students? Now, we also know that the drawbacks of Werner's theory is it never explained the type of bond formed. It never explained the reasons behind the hybridization. All these points it has never explained. So to overcome those, we have discussing the valence bond theory. In the valence bond theory, it will explain hybridization. It could explain the types of bond form and different other principles. In the valence bond theory, if you are looking at the hybrid orbitals, the what type of hybrid orbitals are available, they are actually determined by the ligand. If you have a strong field ligand, it can pair the inner d electrons and make the inner d orbitals available for the hybridization. If it is a weak field ligand or weak ligand, it cannot pair the inner d electrons and it cannot make the inner d orbitals available. So based on the ligand only we are going to get whether the hybridization is sp3d2 or d2sp3, sp3d or dsp3 or sp3 or dsp2. If we have a strong ligand, it can make the inner d orbitals empty. If the inner d orbitals are empty, they can be available for the hybridization. They can be available for the hybridization. If the inner d orbitals are not empty, they are not available for hybridization. But the point you need to understand carefully is, if you study valence bond theory in your chemical bonding, there what we have told you, like for CH4, if you say, we have 1s2, 2s1, 2px1, 2py1, 2pz1 as the electronic configuration of carbon in the excited state. In the excited state, what is the electronic configuration of carbon? 1s2, 2s1, 2px1, 2py1, 2pz1. What is now going to happen? Step 1, the similar energy atomic orbitals will intermix. Intermixing is nothing but hybridization. So which will intermix now? 2s, 2px, 2py, 2pz. All of them will intermix to form how many hybrid orbitals, students? 2s, 2px, 2py, 2pz. They intermix to form 4 hybrid orbitals. What are those hybrid orbitals? sp3 hybrid orbitals. 2s, 2px, 2py, 2pz will intermix to form 4 sp3 hybrid orbitals. After these hybrid orbitals are formed, what is now going to happen? What is now going to happen? What after the hybridization? They directly overlap or they arrange themselves in the minimum repulsion state?
Arrange themselves in minimum repulsion.
Arrange themselves in minimum repulsion state. We write the electronic configuration of carbon. From the electronic configuration of carbon, you have seen the available atomic orbitals for hybridization. Yes or no? Available atomic orbitals for hybridization. From the available atomic orbitals, we have just intermixed them to form the
Arrange
rest.
themselves in minimum repulsion.
Yes, very good. Arranging themselves in the minimum repulsion state. Now the question what I am asking is, why do they arrange in the minimum repulsion state?
Because
It
of
offers
stability.
more stability.
Because of gaining stability. Now look at the atomic orbitals available for hybridization in our case. Like, let us go back to the previous slides just for a second. Yeah, we have this slide, right? In FeCl6 3 minus, Fe plus 3 provides 6 vacant orbitals. We have Fe plus 3 means we have 3d5 electronic configuration. We have 4s, 4p and 4d which are empty. In the 4s you do not have electron. In the 4p also, 4px, 4py, 4pz you do not have electrons. In the 4d we have chosen 2 d orbitals. Yes or no? In the 4d we have 2 d orbitals. If you look at the atomic orbitals, 4s, 4px, 4py, 4pz, and in the 4d subshell we have 4 d orbitals, like 5 d orbitals are there. Out of those, 2 d orbitals are chosen. 4s, 4px, 4py, 4pz, and 2 more d orbitals from the 4d, they are actually intermixing to form sp3d2 hybrid orbitals. Now the question is, why they have to arrange in the minimum repulsion state? Because they do not have any electron. Do they have an electron? 4s, 4px, 4py, 4pz in the 4d 2d orbitals?
No.
In the CH4, whatever the atomic orbitals involving in the hybridization, like 2s, 2px, 2py, 2pz, they have one electron each. So there is a point, like if you say there are 4 sp3 hybrid orbitals formed and they are arranging in the minimum repulsion state, then that is logical, because electron repulsions are there. So in the minimum repulsion state they arrange. But here, do the vacant orbitals, do they have electron first of all?
No, sir.
If they do not have
No, sir.
electron, then why should they arrange in the minimum repulsion state?
So they have different energies, no?
Yeah, they are intermixing.
No,
That
sir.
so they are intermixing. That is fine. 4s, 4px, 4py, 4pz in the 4d, 2 4d orbitals. But you need to understand, it is not same like your chemical bonding. In the chemical bonding, the hybrid orbitals are formed. Whatever the hybrid orbitals form, they will arrange in the minimum repulsion stage. Then they overlap with the atomic orbitals or hybrid orbitals from the other atoms. Here, what is going to happen is, whatever the overlapping is going to be happening, since the 6 sp3 d2 hybrid orbitals are formed, they are getting electrons from Cl minus, right? As soon as they get electron, they distribute in space in the minimum repulsion direction. That is actually happening. The sp3 d2 hybrid orbitals are formed and they are simultaneously getting electrons from the ligands. As soon as they get electrons from the ligands, they try to arrange themselves in the minimum repulsion state. But they do not have electrons by themselves. The vacant orbitals do not have electrons by themselves. Is that point clear?
Yes, sir.
Yes. Yeah, Keshav, you will get all that information in the WhatsApp group. Okay. So this was the point we are looking at. Some special cases, special points. With the 4D and 5D, all ligands behave as strong field ligands. Write down these special points or exceptional cases. Exceptional cases. With the 4D and 5D, all ligands behave as strong field ligands. If the inner d orbitals are 4D or 5D orbitals, then all are going to be strong field ligands only. With the cobalt plus 3 ions, H2O, C2O4 2 minus behave as strong field ligand, like we have seen earlier. Like C2O4 2 minus H2 up to here, what we have said? Up to H2O we have weak field ligand, right? But with the cobalt plus 3 ion, with the cobalt plus 3 ions, H2O C2O4 2 minus behave as strong field ligand. With Fe plus 2 Mn plus 2, NH3 acts as weak field ligand. NH3 is a strong field ligand generally. Nitrogen donors or carbon donors, they are strong field ligands. Yes or no? NH3 is a strong field ligand. But with Fe plus 2 and Mn plus 2, NH3 acts as weak field ligand. With the nickel in the plus 4 state, F minus behaves as strong field ligand. All of you write down this. With Na plus 4 ion, F minus is a halide ion. Halide ions are weak field ligands. But with the nickel in the plus 4 state, halide ions behaves as strong field ligands. Not all halide ions, F minus. These are the exceptional cases because whatever the spectrochemical series we have given, that is not decided based on a single factor. It is obtained experimentally. It is by a result of many factors. Like the ligand is donating electrons means it is donating electrons, the metal ion is accepting electrons, everything is fine, but in between the ligand going to the metal ion, there are a lot of solvent molecules which are going to be affecting the movement of this particular ligand. Yes or no? So the hydration enthalpies, the ionic mobilities, the mobility of these molecules, all these are going to be decided or taken into account. Is that clear, students?
Yes, sir.
Yes.
Yes, very good. So let us now understand our concepts of VBT along with the exceptional cases. So first simple, K4FeCN6, Cn minus is a monodentate ligand and a strong field ligand. Cn minus is monodentate. Monodentate means it will form only one coordinate bond. Electronic configuration of iron, we know 26 is the atomic number. So argon 18, 18 plus 2 plus 6, 26. Argon 36, 4s2. That is the electronic configuration of your iron. Oxidation state of iron here is, we have FeCN6
Plus 2.
yeah, whole 4 minus ion, 1 iron, so 1 into X, 6 ionides, 6 into minus 1, that should be is equal to minus 4. So X should be plus 2. So Fe is in plus 2, that means we have to remove 2 electrons. Those 2 electrons have to be removed from the outermost shell only. So in the outermost shell, you have electrons in the 4s, so you have to remove electrons from 4s. So argon 36, 4s0. So this is the electronic configuration of Fe plus 2 ion. Now write down the arrangement of electrons. We have argon. Argon is all the inner shell electrons. So in the next 3d6, so you have to remove, you have to place 6 electrons in the 3d subshell. Follow Hund's rule. 1, 2, 3, 4, 5. 6th electron is going to be paired. 4s empty, 4p empty, 4d is also empty. So now what will happen? We have how many ligands? 6 ligands are there. 6 Cn minus provide 6 into 2, 12 electrons. So Fe plus 2 should provide 6 vacant orbitals. 6 vacant orbitals to accommodate 12 electrons. What are those vacant orbitals? It can be 4s, 4p, 4d, or 3d, 4s, and 4p. But Cn minus is a strong field ligand. So due to the presence of strong field ligand, what happens? The pairing of electrons occurs. If the electrons pair up, what will happen now? We have 2 d orbitals in the 3d subshell. They are empty. So what are the available orbitals now for hybridization? D2sp3. That means 2 d orbitals from the 3d subshell, 1 s orbital from the 4s subshell, and 3 p orbitals from the 4p subshell. So what is the hybridization? D2sp3, that is the hybridization. So Cn minus will now provide electrons to every D2sp3 hybrid orbital. So Cn minus, each Cn minus is giving 2 electrons. So 6 electrons given to which hybrid orbitals? D2sp3 hybrid orbitals. D2sp3 or sp3d2, what is the shape? Shape of this molecule, shape or geometry? D2sp3 or sp3d2, shape or geometry is going to be octahedral. What is hybridization? Hybridization D2sp3. And what is going to be the type of complex? Inner orbital complex or outer orbital complex?
Inner orbital.
Inner orbital.
Very good. Low spin complex or high spin complex?
Low
Low
spin.
spin.
Low spin complex.
Low spin complex. Okay, whenever you look at the complex, you have to be in a position to comment on its shape, hybridization, type of complex, and low spin or high spin. And what about magnetic nature? Paramagnetic or diamagnetic?
Diamagnetic.
Diamagnetic.
Diamagnetic means it is not going to be, it will be repelled by the external magnetic field weakly, right? Yes. So this is how you need to understand the complex K4 efficiency. Whenever a complex K4 efficiency has been given to you, what is the hybridization, what is the shape, what type of complex it is, low spin or high spin, and magnetic nature, all these points you have to understand. If you are done with the noting part, please let me know, students. I'll proceed. All of you, if you are done with the noting part,
Done,
please.
sir.
Done? Okay, fine. So this is your Fe K4 Fe6. The Fe plus 2 ions will have coordinate bonds with the 6 cyanide ions, and you have 4 K plus ions as the counter ions. Next example, K4 FeCl6. Same, in the same way we can write Fe, first write the electronic configuration of iron. Cl minus is a what type of ligand? Monodentate ligand and weak field ligand. Monodentate and weak field. Weak field ligand means no pairing will occur. Electronic configuration of iron, argon 3d64s2, Fe plus 2 will be argon 3d64s0. Because we have removed 2 electrons from the Fe to form Fe plus 2. But Fe plus 2 is not a simple ion now. It is present in the complex ion. Yes or no? K4 FeCl6. It dissociates to give 4K plus plus FeCl6 whole 4 minus. Fe plus 2, we have written argon 3d64s0. So 3D, 4S, 4P, 4D. And you have to write the D6 electronic coefficient. D6 means one electron into each d orbital, then the 6th electron will be paired up. After 3D you have 4s, then 4p, then 4d. Fe plus 2 argon 3d64s0. After 3D you have 4s, 4p, 4d. In the 4s or 4p or 4d you do not have a single electron. And now we have Cl minus, which is a weak field ligand. Weak field ligand cannot experience or cannot repel the inner d electrons of a 3D subshell greatly. That means it cannot pair these electrons. So what type of complex it is? Inner orbital or outer orbital?
Outer orbital.
Outer
Outer
orbital.
orbital complex. Low spin or high spin?
High
Spin
spin.
complex.
High spin complex. What is the hybridization? Hybridization.
sp3d2.
sp3.
sp3d2.
Very good. What is the shape?
Octahedral. Outer
Octahedral.
octahedral.
Octahedral. What about magnetic nature?
Paramagnetic.
Paramagnetic.
Paramagnetic. Very good, all of you. So it is going to be outer orbital complex, high spin complex, sp3d2, octahedral, and paramagnetic. No pairing occurs due to the presence of weak field ligand or Cl minus. So only 1 4s, 3 4p, and 2 4d. These atomic orbitals involved in hybridization to form sp3d2 hybrid orbitals. How many are formed? 6 sp3d2 hybrid orbitals are formed. What they'll get, they will be gaining electrons from the 6 chloride ions. So 6 chlorides will be donating 2 electrons to every sp3d2 hybrid orbital, leading to the formation of sp3d2 hybridization octahedral complex, paramagnetic outer orbital complex. I hope it is very clear to you because you are only answering all the questions. Yes or no?
Yes, sir.
Yes. and FeCl6, K4 FeCl6 will have octahedral, so that is the shape. Next students, NaCl4 2 minus. Try to answer this. NaCl4 2 minus. You try to answer the hybridization. What is the hybridization? Write the electronic
sp3 sp3 hybridization.
sp3 shape.
A trigonal planar. Oh, a tetrahedral. Sorry, tetrahedral.
Okay. Yeah, just let us proceed with the same logics. Cl minus is a monodentate ligand and weak field ligand. Electronic configuration of nickel. Argon 3d8 4s2. Nickel in the +2 states. Argon 3d8 4s0. So 3d8 means we have to fill the electrons in the 3d subshell. So each d orbital gets 1 electron, then the pairing starts. After 3d you have 4s and 4p. No pairing occurs due to the presence of weak field ligand. So no pairing occurs means you will have 4s and 4p orbitals only available, vacant orbitals. So they will be involving in the hybridization to form 4 sp3 hybrid orbitals. What are they going to form? 4 sp3 hybrid orbitals, and only outer orbitals are involved in the hybridization. So outer orbital complex and sp3, that is going to be tetrahedral. Yes or no? sp3 means tetrahedral. Whether it is G2 sp3 or sp3 d2, it is obviously octahedral. sp3 means tetrahedral. dsp2 means dsp2.
Square planar.
Square planar. Okay. sp3 means tetrahedral. dsp2 means square planar. Here you are going to get sp3 tetrahedral paramagnetic complex or not, because you have unpaired electrons. Can I proceed further, students? Yes or no?
Yes, sir.
Yes, sir.
Yes. Next example, NaCl4 2 minus. You can expect what is the hybridization now?
dsp2.
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 dsp2 means what is the shape?
Square planar.
Square planar.
Square planar.
Okay, very good. So in this molecule, in NaCl4 2 minus, what is the sum of MLL LML bond angles? I'll just give a question. In NaCl4 2 minus, sum of LMLL. L means ligand, M means metal, L means ligand. Sum of 120 degrees, 90 degrees, and 180 degrees ligand metal ligand bond angles is how many? In this complex, question is like this. In the complex of NaCl4 2 minus, the sum of 120 degree angles, 90 degree angles, and 180 degree angles in the what are those angles? The angles of ligand metal ligand. These bond angles are how many?
For 90 it is 1 and for 180 it is 2.
For 90 it is 1, for 180 it is 2. Sure?
Sir, you are asking about bond angles, right? Between two ligands and metal.
Ligand metal ligand. Ligand metal ligand angles.
Two 180.
First let us figure out. Cn minus is a monodentate ligand and strong field ligand. So what is the electronic configuration of nickel? Argon 3d8 4s2. Nickel plus 2 will be argon 3d8 4s0. We have removed 2 electrons from the 4s. We know the electronic configuration is 3d 4s 4p. And after this, after pairing, why pairing occurs? Because Cn is a strong field ligand. So they will pair up. So if they pair up, you will be getting one 3d orbital which is going to be empty. So for the hybridization, what are the atomic orbitals available? 1 3d, 1 4s, and 2 4p. So dsp2 will be the hybridization. dsp2 will be the hybridization, and what is going to be shape? Square planar, and it is a lower orbital complex. Yes or no? And it is going to be diamagnetic in nature. Because of pairing, spin has been decreased, so low spin complex. Now, if I am asking about sum of 120 degree, 90 degree, 180 degree bond angles, ligand, metal ligand, this angle is 90 or not? Ligand, metal ligand, this angle is 90 or not?
Yes, sir.
Ligand, metal ligand, this is 90 or not? Ligand, metal ligand, this is
Yes.
also 90. So, can I say ligand, metal ligand, this is 180 or not? Also, I have
Yes, sir.
ligand, metal ligand. This is also 180. So, can I include again this angle as 180? Or since I have already taken this angle as 180, that is also included automatically.
Yes, sir.
If I am saying that, if let us give you numbers L1, L2, L3, L4. This is L2, this is L3. This is L1, this is L4. L1, L2 ligand metal L3. If they form an angle of 180 degree, that automatically means L3 metal L2, they will also at 180 degree or not? So if you are counting this angle, you should never count that angle. That is counting the same angle twice. It becomes counting the same angle twice. So how many 90 degree angles we have? 4 90 degrees. How many 180 degree angles we have?
2.
2 180 degrees. The same thing you can do for K4 FeCl6 or not? Or K4 FeCl6? K4 FeCl6. Same question. This is a complex given to you. This was a complex given to you. Calculate the sum of 90 degrees, 180 degrees, 120 degrees bond angles.
It has 3 120 octahedral.
Octahedral, no. Octahedral means we have
490 degree, 690 degrees.
how many 90
690
degrees are there?
690 degree.
How many 90 degrees angles are there?
All are 90.
Sir, 80 degree.
90 degree angle.
90 degree angles will check out. So can I say, so this is like a paper, no? I'll have a paper here. This is like a paper, no? At the center you have metal. L1, L2, L3, L4. 4 ligands at 4 vertices of the square. 1 ligand above, 1 ligand below. What are 90 degree angles now? This ligand which is above, ligand, metal, ligand. This is 90 or not? Because this is perpendicular. This is like this. Yes or no? So this ligand,
Yes.
ligand which is above, that will be forming how many 90 degree angles with these 4 ligands? Ligand, metal, ligand 1, ligand, metal, ligand 2, ligand, metal, ligand 3, ligand, metal, ligand 4. So top ligand is going to have how many 90 degree angles?
4.
4.
4.
Same way bottom ligand will have ligand, metal, ligand, ligand, metal, ligand, ligand, metal, ligand, ligand, metal, ligand. How many?
4.
4.
4 plus 4. And do we have any more 90 degree angles?
So the one on the plane, 4 of them on the plane.
Yes or no? 4 are on the plane. Ligand, metal, ligand 90. Ligand, metal, ligand 90. So 4 more on the plane. And 180 degrees, how many? 120. Do we have any 120? Any 120?
No, sir.
No, sir.
No 120. Okay, these are all 90 degrees. 120 degrees 0. Any 180? How many 180 are there?
3. 3.
This is 180. This is 180. This is also 183. 3 will be 180. So total is how many? Sum of
15.
15. So like that questions can be asked. If the sum of 90 degrees, 120 degrees, 180 degrees bond angles in the complex K4 FeCl6 is X. K4 FeCl6 is X. And the sum of 90 degree, 120 degree, 180 degree bond angles in a complex, in a trigonal bipyramidal complex is Y. Next question is, next same question. So in the same question, if the sum of 90 degree, 120 degree, 180 degree bond angles in K4 FeCl6 is X, and in a square or trigonal bipyramidal complex is Y, and in trigonal bipyramidal complex is Y, what is X plus Y? What is Y? Trigonal bipyramidal complex to consider. Any complex which is having sp3d hybridization or dsp3 hybridization. In try to figure out in the trigonal bipyramidal how many 90 are there, how many 180 are there, how many 120 are there. Trigonal bipyramidal.
690, 3 120, and 2 180. Only 1 180.
So 90 degrees you have to figure out. So the top ligand,
Six-
metal ligand 190, ligand metal ligand second 90, ligand metal ligand third 90. So this one will have 390 with these 3 ligands. This one will also have 390 with these 3 ligands. So 3 plus 3, 6 will be 90 degrees. What about 120? 120 you can have within the trigonal plane. 3 will be 120. What about 180? 180 will be only 1. 1 in 80. So how many in total? Sum? Sum is 10. What is sum? Earlier the sum is 15. So what is x plus y means? X plus y means 25. Like that questions can be developed, not like straightforward questions. Fine students, let us proceed further. This is your NaCN4 2 minus. FeCO5, try to figure it out here. FeCO5, try to write the electronic configuration of iron. Because FeCO5 is an example of your sp3d complex where I have taken the earlier case. Like sum of angles we have figured out now. In the NaCN4 2 minus, it is a dsp2, K4 FeCl6. They can ask a question. The sum of 90, 120, 180 degree angles in K4 FeCl6 is X, and in FeCO5 is Y. What is X plus Y? So let us now understand FeCO5. Fe electronic configuration is argon
3d6 4s2.
4s2. In FeCO5, what is the electronic configuration? What is the oxidation state of iron? One
Zero.
iron is there, let us say X state. So 1 into X, 5 carbonyls, 5 into 0, that will be 0. So X is equal to 0. So metal is in 0 oxidation state. So argon, then you have argon. This is your 3D. Then you have 4s. Then you have 4p. And then you have 4d. 3d6 electronic configuration, write down. 1, 2, 3, 4, 5, 6. This is a scenario of Fe, and you also have 2 electrons in the 4s. You also have 2 electrons in the 4s. Yes or no? Because it is not Fe plus 2 ion, it is Fe only. In FeCO5, we have iron in the 0 oxidation state. So we have electrons in the 4s. Now what will happen, students? CO is a strong field ligand or weak field ligand? CO.
Strong field ligand.
Strong field
Strong
ligand.
field.
Because of that strong field, what is going to happen with the inner electrons of 3D? They are paired up or not?
Yes, sir.
They are going to be paired up. Like you can say, we can say these 2 electrons paired up, these 2 electrons paired up. If they pair up, what is happening? If they pair up, what is going to happen? If they pair up, what will be happening?
Vacant orbitals will form.
You have 1, 2, 3, 4, 5, 6. You have 4s. You have 3d. You have 4p also. You have 4d also. And now can we say 2 electrons are there in the 4s? Will they be transferring to 3d or not?
Yes, sir.
Yes, or that will also
Yes,
happen.
they will join to the day.
So if they go into the 3d, what is going to happen? You have one d orbital empty or not?
Yes.
So is it
Yes, sir.
sp3d or dsp3?
DSP3.
It is going to be dsp3, not sp3d. You make a change here. It is dsp3. So one 3d orbital, which is inner orbital, that is also empty. So the 4s is empty. In the 4p, you have 3p orbitals which are empty. So it will be dsp3. dsp3 again will have trigonal bipyramidal only. Shape is going to be trigonal bipyramidal. Inner orbital or outer orbital? Inner orbital is used. So inner orbital complex, yes or no? Because the inner 3d subshell have seen the pairing of electrons, and they have also seen the pairing of electrons, and they have the inner orbitals which are involving in hybridization. So obviously inner orbital complex. Low spin or high spin, pairing happened, so low spin complex. Diamagnetic or paramagnetic, there is no unpaired electron, so diamagnetic in nature. So dsp3 trigonal bipyramidal inner orbital complex, low spin complex, and diamagnetic. That is the complete information of FeCO5. Is that clear, students?
Yes, sir.
Yes,
Yes, sir.
very good. Now try to write down PtCl4 2 minus. PtCl4 2 minus. So if you look at the electron, DSP2 or sp3?
DSP.
Why?
So it is
Platinum.
40,
Platinum
5D.
Cl negative,
Platinum
Cl
5D.
access strong
Yeah,
field
Cl
ligand.
minus acts as strong field ligand. If it is for a 4D or 5D, all ligands will be behaving as strong field ligands. So for in the platinum, you have platinum. These not a 3 series elements. You do not have 3D inner orbitals. So Cl minus will be acting as strong field ligand. Strong field ligand means pairing of electrons occurs. If the pairing occurs, platinum belongs to which group? Above platinum, what do you have?
Nickel.
Nickel, right? D8, right? So we have D8 configuration. So D8 means 1, 2, 3, 4, 5, 6, 7, 8. So these two are going to be paired up now. So you have one d orbital empty. Similar to nickel, I'm writing. So in the D8, in the platinum also you'll be having D8, where one d orbital is going to be empty. So dsp2, that will be the, because we have 4 ligands only. Each ligand will give 2 electrons. 4 ligands will give 4 into 2, 8 electrons. 8 electrons can be occupied by 4 vacant orbitals. So 4 vacant orbitals, what are those? One 3D, like 1D, 1S, and 2P. So since it is not a 3D series elements, all the ligands act as strong field ligands. So DSP2 means square planar, and inner orbital complex, because pairing happened and inner orbitals has been used. Because pairing happened, low spin decreased, and no unpaired electrons, so diamagnetic. Got this? PtCl4
Sir,
2
I
minus.
have a doubt.
Yes, Faizan.
Sir, platinum's electronic configuration is 3D94S2. In D block, we have studied it's an exception in the regular electronic configuration. Platinum and
Okay.
palladium both. So its electronic configuration is 3D 94S 49 5S1.
What is that? That is in the scenario of single platinum. But here we do have a single platinum or the complex ion.
Complex ion.
In the complex ion, the ligands are going to be determining how the electrons have to be arranged. Okay.
Okay. Okay.
That is the single ion which was present in aqueous solution. There you have a different scenario, but all these are complex ions. In the complex ion, we have a ligands forming a coordinate bonds. So ligands ultimately determine the positioning of the electrons in the metals. So that is why this is the correct way. Okay.
Okay, sir.
So DsP2 square planar inner orbital complex, low spin complex. Try to figure out this one, students. FeH2O taken 5, NO. FeH2O taken 5, NO, SO4. It is a brown ring complex. What is the oxidation state of iron here?
Plus 2.
Plus 1.
Plus
Write the
2.
electronic configuration of iron. Iron will be in which state?
No, sir,
Argon.
plus 1.
Yeah, electronic configuration you write down. Argon 3d6 4s2. Yes or no? Argon 3d6 4s2. So what is going to happen now? Iron is in +1 state. Fe +1 means argon 3d6 4s1. Write the electronic configuration. Argon 3d6 4s1. You will be having 1, 2, 3, 4, 5. The sixth electron will be in the 3d only. In the 4s, you have 1 electron. Yes or no? In the 4p, you have no electrons. In the 4d also, you have no electrons. In the 3d, you have 3d6 electronic configuration. So this is the scenario. H2O taken 5 NO. H2O is a weak field ligand or strong field ligand? NO, H2O and NO. NO. NO means
NO
what?
is a strong field.
NO, nitrogen donor. Yes or no? So strong field ligand. So what will now going to happen is, you will be having pairing of electrons. You will be having a pairing of electrons. We have 5 weak field ligands and only 1 strong field ligand. The pairing of electrons is going to happen. From the 4s, the electron goes into the 3d. So that electron is going to be paired up. Write down. This is an exception and important case. From the 4s, the electron goes into 3d and it will be paired up. And you have 4s empty now. 4p is also empty. 4d of course will be empty. 4d of course it would be empty. Now you may ask a question, sir, why are you not pairing up the remaining other electrons? You are saying like number of unpaired electrons is 3. sp3d2 like 4s 4p 4d, 1 4s 3p orbitals from the 4p and 2 from the 4d are hybridized. So sp3d2 is the hybridization. sp3d2 octahedral will be the shape. And which orbitals are involved in the hybridization? Outer orbitals. So outer orbital complex. And it has unpaired electrons, so paramagnetic. But you may argue, sir, why are you not pairing up this electron? If it paired up, what is going to happen? If it paired up, what will happen now, students? This is the scenario or not? This is the scenario or not? If it paired up, the electron, out of 3 unpaired electrons, 1 unpaired electron got paired with the other. So you have only 1 unpaired electron in the 3D now. 4s is empty, 4p empty, 4d is also empty. And we require how many? We require how many vacant orbitals in the metal?
5.
5 or 6?
6.
We require how many vacant orbitals? We require 6 vacant orbitals in the metal to accept the 6 into 2, 12 electrons from the ligands. So if you require 6 vacant orbitals, you cannot have one 3d orbital. Like we require 6, right? So 4s and 4p, they will include 4. Either you have to include both 3d orbitals or you have to include both 4d. There is no possibility of hybridization happening with one 3d and one 4d because of energy difference. That is why pairing is not going to happen. Understanding this point or not? And
Yes,
also we
sir.
have only one strong field ligand. If you have all the strong field ligands, then the pairing possibility is high. We have only one strong field ligand, and the other way is, if that pairing happens, you will be having one 3D empty and one 4s 3 4p, and you have to involve one more 4D. So one 3D plus one 4s plus 3 4p plus one 4D. This is not the possible, not at all possible, not possible because of energy difference, not possible because of high energy difference. The atomic orbitals which are going to be hybridized, they should have similar energy. So here they will not be having the 4D, one 4D and one 3D, they cannot intermix. So that is not possible. So that is why you do have 3 unpaired electrons in the metal itself. The outer orbital complex is going to be formed. So sp3d2 octahedral outer orbital complex, paramagnetic nature. This is the correct. This is the correct information regarding your Brownian complex. Got it, students?
Yes, sir.
FeH2O taken 5NO, you cannot involve one 3D atomic orbital and one 4D atomic orbital in the hybridization because of energy difference. You can involve both the 3D or you can involve both 4D, but both 3D is not possible. By because you have such an electronic configuration. This is one of the reason, and the other reason is you have only one strong field ligand NO. Remaining 5 H2O molecules are weak field ligands. So that is about your Brownian complex, oxidation state of Brownian complex, and the respective structure, shape, and magnetic nature. Let us now look at transference of electrons. All of you just let me know if you are done. You can just type letter S in the comment section. Yes, very good. Transference of electrons. Whenever we have D9 configuration, in the presence of strong field ligand and coordination number 4, one electron shift into the 4p subshell. Write down this. First you write down this. The electrons are going to be transferred when D9 configuration, in the presence of strong field ligand and coordination number 4, one electron shift into 4p subshell. D7 configuration, in the presence of strong field ligand and coordination number 6. Coordination number 4 means like similar to your tetrahedral complexes, tetrahedral or square planar. Coordination number 6, octahedral complexes. D7 configuration, in the presence of strong field ligand and coordination number 6, one electron shift into 4D subshell. One electron will shift into the 4D subshell. How that is going to happen, how the shifting is going to happen, let us understand now. Let us take a complex. CuNH3 taken for 2+. What is the electronic configuration of copper here? First, NH3 ammonia is a monodentate ligand. Yes or no?
+2.
Yeah, ammonia is a monodentate ligand and it is a strong field ligand. And copper is in +2 state. Cu is in +2 state. Electronic configuration. Copper means you have
3D10 4s1.
yeah argon 3d10 4s1. Cu +2 will be argon 3d9 4s0. So we have 3d9 scenario. Write down the electronic configuration. So you will get argon 3d10 4s1. Cu +2 will be argon 3d9 4s0. 3d9. So 1, 2, 3, 4, 5 electrons in 5 different d orbitals. Then the pairing of electrons happen. After 3d you have 4s and 4p. In the 4s you do not have electron. In the 4p also obviously no electrons are there. Now what will happen? NH3 is what type of ligand? Monodentate ligand and strong field ligand. Is there a possibility of pairing here? Is there a possibility of pairing?
No, sir.
No, sir.
No possibility.
No, sir.
So yeah, now what is going to happen? Transference of electron occurs. One electron from the 3D will shift into 4p now. Look at that. How interesting it is. From the 3D, after 3D you have 4s, you have 4p, but Nothing like that. From the 3D, the electron is going into the 4p. So what is going to happen now is one electron from 3D, it will go into the 4p. And because of the transference of electron, you will get one 3D atomic orbital, one 4s, and two 4p, which are going to be vacant now. And because of that, what is going to happen? Because of that, you will be having dsp2 or sp3 hybridization.
DSP2.
Yes. If you simply write 3D 4s 4p, since there is no possibility of pairing, then you cannot pair. If you cannot pair, you will simply involve the hybridization of 4s and 4p, and then you will be calling sp3 hybridization, which is wrong. Why? Because of a strong field ligand, because of ammonia, which is a very strong field ligand, the what happened? Because of ammonia, which is a very strong field ligand, what happened with respect to ammonia? It can make the 3D electron go into the 4p and make the inner d orbital available for hybridization. Why? Because of its more repulsion. Why? Because ammonia is a strong field ligand, right? So now ammonia, 4 ammonia will be donating electrons to the 4 dsp2 hybrid orbitals. So dsp2 means square planar. So if you do not do the transference of electron, you will write sp3 and you will write tetrahedral, which is wrong. And it is paramagnetic. Yes or no? It is a paramagnetic complex because we have unpaired electron. It is inner orbital complex because inner d orbitals has been used in the hybridization. And we cannot comment on spin. We cannot say it is a low spin complex or high spin complex. Why? Because pairing never occurred. So no comment on spin. Cannot comment on spin. Spin not defined. Because if it is a low spin, high spin, when you can define? When the pairing happens, spin decrease, that is why low spin. When the pairing did not occur, high spin. But here, although NH3 is a strong field ligand, the spin is not decreased. That is why we cannot comment on spin. In case this option is not there, and they have given low spin, that won't be given because spin we cannot define. Okay, that's like a controversy. Are you getting this, students?
Yes, sir.
Yes. So this is an important examples, like transference of electron is possible for the D9 configuration. Yes, D9 strong field ligand. So D9 strong field ligand, coordination number 4. So what happened now? Transference occurred. Next example, what I have told you?
D7 configuration.
D7 configuration, strong field ligand, coordination number 6. Yes or no? Let us look at that example as well. Complex are not given, but you can just write down the d orbitals and figure it out by ourselves. So let us write D7 configuration. D7 means you will be having 1, 2, 3, 4, 5 d orbitals. This is 3D, 4s, 4p, and 4d. D7 configuration. So 1, 2, 3, 4, 5, 6, 7. Yes or no? This is D7 configuration. And now you have to do the strong field ligand is there. So pairing of electrons you can do. If you pair the electrons, what will happen? These two electrons can pair up. So you have 1, 2, 3, 4, 5, 6. Seventh electron is actually again unpaired. Although it is a strong field ligand, you still have one electron which is unpaired. You cannot pair this electron. Can I pair this electron? I can't pair. Can I involve 1 3D plus 1 4s plus 3 4p plus 1 4d? Can I have this possibility?
No.
No, we cannot have this possibility. If you are involving d orbitals, both the d orbitals should be from the same subshell, either from the 3D or from the 4D. You cannot have one d orbital from the 3D and other from the 4D. This is not possible. Since it is also not possible, and we require 6 vacant orbitals, so what is going to happen? Since the strong field ligand is already there, so this electron will be going into the 4D. So in that case, what will happen? You have 1, 2, 3, 4, 5, 6. You have 2 3D vacant, 4s vacant, and 4p vacant. 4p is also vacant, and 4d, 2 3D, 1 4s, 3 4p. Yes or no? And what happened to the electron? The electron went from the 3D to the 4D. So now what is the hybridization? D2sp3 is hybridization. Again, everything is same. D2sp3 hybridization. What is the shape? Octahedral. What type of complex it is? Inner orbital complex, because we are using the inner orbitals. And what is the magnetic nature? Paramagnetic, because we have an unpaired electron, but we cannot again comment on spin. It can't be a low spin or high spin complex because pairing is never happened, even though we have a strong field ligand. Understood this point, students?
Yes, sir.
Yes. So these are the different cases from your valence bond theory. What are limitations? First, it is not explaining any color, and no explanation for strong field ligand and weak field ligand. That is not even explaining crystal field theory. The next theory also cannot explain why a complex is strong field ligand, why a complex is weak field ligand. Yes or no? Because that is completely obtained from spectrochemical series. No explanation for stability of complexes. Which complex is more stable, which complex is less stable, that is also not explained. Write down this. Limitations of VBT are, it could not explain color of the complexes, which is the main drawback, because most of the complexes are colored in nature. If you cannot explain the real scenario, which I am seeing daily directly, if I am dealing with complexes, I am seeing its color. Yes or no? Which is seen for all the complexes, most of the complexes. If all the complexes and most of the complexes are colored in nature, and we have developed a theory which is unable to explain the color, then that is not an issue. That is not a good theory. We have to develop or modify our theory. Yes or no? So that is why the next theory comes into picture, crystal field theory. Crystal field theory, CFT. According to crystal field theory, all the ligands are point charges. You know this postulate? Central metal ion is considered as a positive point charge. Anionic ligands are negative point charges. Neutral ligands has a point dipole, and attraction between metal ion and ligand is electrostatic in nature. From this point, like what is a metal ion? Metal ion is Mn plus ion. Ligands are there L1, L2, L3, L4, L5, L6. 6 ligands are there. Let us consider octahedral complex. We have central metal ion L1, L2, L3, L4, L5, L6. 6 ligands are there. Now, just to talk, students, if the central metal ion is already positively charged, point charge, ligands are point charges, what type of attraction would be there between point charges? Electrostatic or not?
Yes, sir.
So what type of bonding is present between the ligand and metal according to CFT?
Ionic.
Ionic.
Ionic, or completely we have electrostatic force of attraction between electrostatic force of attraction is present between central metal ion and the ligand. From this, can you quote any drawback of CFT from this first statement itself? Ligands are again 3 categories, right? Positive charge ligand, negative charge ligand, neutral ligand. If you have a negatively charged ligand, it can be considered as a negative point charge. According to this theory, anionic ligands are negative point charges. Neutral ligands are positive ligands. They are considered as point dipoles. They are considered as dipoles. Now consider a ligand like F minus. F minus is a negatively charged ligand or not?
Yes.
Yes.
So it should be considered as a negative charge. So consider any metal ion. Metal ion is positive charge. F minus is negative charge, negative charge, negative charge, negative charge. Consider ammonia. Ammonia is a neutral ligand or not?
Yes.
Ammonia is neutral ligand. Neutral ligand should be considered as what? Neutral ligand should be considered as point dipoles. Point dipoles. So if you look at the electrostatic force of attraction between a positive charge and F minus, which is a negative point charge, and between a point positive charge and NH3, which is a negative charge dipole, where the electrostatic force of attraction should be high.
Anionic point charge.
Yes or no? So if you have positive, negative, and if you have positive delta minus delta plus, so where the electrostatic force of attraction will be high, students? Obviously, in the case of anionic ligands, this is neutral ligand. So in the case of anionic ligands, the electrostatic force of attraction should be high. The electrostatic force of attraction should be obviously high when compared to the electrostatic force of attraction between a positive charge, positively charged metal ion and your neutral ligand. But among ammonia and F minus, which is a strong field ligand,
NH3 ammonia.
ammonia. From this logic, the anionic ligand should be kept where? In the strong field ligand series? Yes or no? Positive charge, negative charge. From this logic of positive charge, positive point charge having great attraction with point negative point charge, we should categorize all the negatively charged anionic ligands as strong field ligands because more attraction would be there. And obviously, if more attraction is there, they are going to be repelling the inner d electrons greatly. So they should be categorized as strong field ligands. But we know spectrochemical series. In the spectrochemical series, all the negatively charged anionic ligands, they were placed where? In the weak field ligand category. So that is a drawback or not? Right on that point, very logical and interesting point. Okay. Central metal ion is considered as point charge. Anionic ligands are considered as negative charge. Neutral ligands as point dipoles, and attraction between metal ion and ligand is electrostatic in nature. From this, what we can say, students? If anionic ligands were considered as point negative charges, if anionic ligands were considered as point negative charges, then they will repel the inner d electrons of metal ion, inner d electrons of metal ion greatly when compared to the repulsion given by negative dipoles from neutral ligands. From this logic, we can say, from this we can predict all anionic ligands should be strong field ligands. But in reality, most of them are weak field ligands, which is a drawback of crystal field theory, CFT. From the first statement itself, we have understood one drawback of crystal field theory. All of you note down these very logical things. If anionic ligands were considered as point charges, then they are going to be having greater attraction with the metal ion, and they will also repel greatly the inner d electrons of the metal ion. If the anionic ligands are repelling the inner d electrons greatly, they should be strong field ligands. But in reality, what is happening? Most of the anionic ligands are weak field ligands. So that means they are contradictory to each other. So reality is different, and what is explained or what is predicted by CFT is different. So that is a drawback of crystal field theory as well. Is that point clear, students? All of you?
Yes.
Yes, Vaidehi, very good. Now try to understand the splitting of d orbitals in the presence of this octahedral complex. We have a metal ion. In the metal ion, we have 5 d orbitals. What are the shapes of d orbitals? What are the shapes of d orbitals?
Double dumbbell.
Yeah, dxy, dyz, dzx. dxy will have what shape? They have lobes in between the axis or along the axis. Double dumbbell is shape of d orbital, that's fine. But what is the shape of dxy? In between the axis or along the axis, students?
Along the axis. Along the axis.
Along the
In
axis,
between
Faizan?
axis.
It between the
In
In
between.
between it. So if it is xy, between x-axis and y-axis, you have the lobes of d orbitals of dxy. dyz means again in between the axis, but the axes are y and z now. dzx means
In between axis.
in between axis, but the axes are z and x now. dx square minus y square dz square
Along the axis.
Along X and Y.
along axis, dx square minus y square and dz square. dz square will have some electron density present in the xy plane or not? In the form of ring. How are these obtained, students? Have you ever questioned? Sir, how are you saying the shape of d orbital is like this? What, Faizan?
I don't know, sir.
Don't know. So these are how the shape of orbitals have been assigned. What are these orbitals? Every orbital will have wave function psi. Yes or no?
Yes, sir.
Yeah, by solving Schrodinger equation, we are getting psi. Yes, from the Schrodinger equation only, we will be getting all these orbitals and respective shapes. So they are true. So not like arbitrarily given, they are true. So we have metal ion now, central metal ion. Let us consider an octahedral complex. In an octahedral complex, like we have a central metal ion here, and we say this is your x-axis, negative x-axis and positive x-axis, positive y, negative y, positive z, negative z, plus x, minus x, plus y, minus y, sorry, plus y, minus y, plus z, minus z. Now consider ligands are approaching from the x-axis plus x-axis, minus x-axis, plus y, minus y, plus z, minus z direction. So ligands are approaching from 6 directions. X-axis like they are approaching, plus x, minus x. Y-axis from the top and bottom approaching. Z-axis from towards my side and towards your side approaching. And in the metal ion, we have inner d orbitals or not? In the metal ion, we have inner d orbitals. Ligands are approaching along the axis. That is what leading to your octahedral complex. If the ligands are approaching along the axis, and obviously they are going to be attracted with the metal ion because ligands are negatively charged, metal ions are accepting electrons. Ligand and metal, they have attraction. But in the metal, we have d orbitals. The d orbitals of metal and the ligand, they will repel. Electron, electron repel. So the d orbitals, how many d orbitals are there? 5 d orbitals, dxy, dyz, dzx, dx square minus y square, dz square. Out of these 5 d orbitals, which d orbitals experience more repulsion? Ligands are approaching along the axis. So whatever the d orbitals whose lobes are along the axis, they will experience more repulsion or not? Yes or no?
Yes, sir.
Yes, yes, sir.
You consider a metal ion, you consider my wrist as a metal ion, it has its dx square y minus y square orbital whose lobes are along the axis. Ligands are approaching like this. Ligands are positioned like this. Lobe is already along the axis. So repulsion is great, no? So repulsion great means energy will be high. So the 5d orbitals, if you take the 5d orbitals, they will now split into two sets. What are two sets? T2g set and EG set. In the EG set, we have d orbitals whose lobes are along the axis. What are those? Dx square minus y square or dz square. In the T2g set, we have those d orbitals whose lobes are in between the axis. Dxy, dyz, dzx. Understood the splitting or not? We have 5d orbital students. All the 5d orbitals will not experience same repulsion from the ligands. All the 5d orbitals will not experience same repulsion from the ligands. Those d orbitals whose lobes are along the axis, they experience more repulsion when compared to those d orbitals whose lobes are in between the axis. This is a scenario when it is your octahedral complex. When it is your octahedral complex. So let us, can I say, is it noted first? First tell me whether this part is noted or not. All of you note it down and let me know. Is it noted, students? Can I proceed further?
Yes, sir.
Yes, Aishi, very good. Now listen carefully. We have 5 d orbitals initially. The d orbitals which are degenerate in nature. Degenerate means same energy. Initially all the d orbitals are degenerate. Now we are talking about spherical field. Spherical field means what? Because ligands are negative charges, metal ion is positive charge. Around the ligand, around a charged particle, we have some field or not? Like we have a positive charge, it will develop some electric field or not around itself. It doesn't mean like you have a positive charge here and in Mumbai there's a negative charge. The negative charge in Mumbai cannot be attracted towards the positive charge here. That is not possible, right? So around every charge we have some field. The repulsion or attraction is going to be happening only if that particle, if the oppositely charged particle or same charged particle comes into that field. So that is why if we have a spherical field, all the ligands coming from all directions. Now it is not an octahedral field. Spherical field means ligands are coming from all the directions. So it is a degenerate d orbitals. This is a degeneracy still holds in spherical field, because when the ligands are coming from all the directions, like infinite number of ligands are there now. Metal ion is there. They are coming from all the directions, like a spherical ball. At the center of the ball, we have metal ion. At every point of the circumference, we have what? We have ligands. So every ligand will be repelling the d orbitals in equal way. So you have all the d orbitals of same energy now, but high energy. So degeneracy is still there in spherical field. But whenever you have octahedral field, the degeneracy will be disturbed. In the octahedral field, the degeneracy will be disturbed. Degenerate d orbitals in no field. This is the first scenario. When compared to first scenario and octahedral field, the d orbitals still have higher energy or not? When compared to no field, in the octahedral field you have high energy. When compared to no field, in the octahedral field you still have higher energy. So this is your T2G, this is your EG now. Now I want to generate a square planar field. What you are going to do? Any ideas from your side? From the octahedral field, I want to explain the splitting in square planar complex. Like you have studied square planar complex, like NaCN4 2 minus. Just now in the previous valence bond theory, have already told NaCN4 2 minus means cyanide is a strong field ligand. Pairing of electrons occurs in the 3D subshell. So we have dsp2 hybridization. dsp2 means square planar is the shape. That's completely fine, 100% correct. But how the d orbitals are going to be splitted in the presence of square planar field? Any ideas? Any idea, students? Right or wrong? You just say your idea. That's fine. You try to give wrong answer. That's very good. What Ayushi? Now consider. So this is your, at the center of this paper you have metal ion. I'm just making it a square plane. Metal ion is there. Ligand 1, ligand 2, ligand 3, ligand 4, square plane. Forget about square planar complex. Just talk with octahedral complex now. If it is octahedral complex, where do you have ligands? Metal is there. 1, 2, 3, 4. One ligand above, like this. Other ligand below. Yes or no? You can see this or not? Metal ion at the center. 4 ligands are there on the square plane. One ligand above, one ligand below. From the octahedral complex, I want to generate square planar complex. What I have to do? From the octahedral complex, if I want to generate square planar complex, what I have to do? You answer this.
Remove the upper ligands.
The
Remove
axial
the
bond.
above one and below one, right? That's it. So now I am removing the ligands along the z direction. That's it. So if you try to remove the ligands from the z direction, from the octahedral complex, what you are going to develop? You are going to generate a square planar complex. Now imagine your scenario. If you are removing ligands from the z direction, which orbital's energy will be decreased? Energy decrease means repulsion decrease. In the EG set, we have dx square dy square, dx square minus y square dz square. Dz square have lobes along the dz square orbital has its lobe along the z direction. So its a repulsion will be decreased or not? Yes or no, students?
Yes, sir.
Yes. So dz square. So the EG set, which is dx square minus y square dz square, it can't be same now. It will split into, EG will be splitting into dx square minus y square, which should be highest now, and dz square, which should be low. T2g will be same or it will also split again?
It will be same.
It will be same. dxy, dyz, dzx. Look at now. dxy, dyz, dzx. I am removing ligands. I am removing ligands along the z direction. So dyz, dzx. Are they going to be affected or not? In the yz, what do you mean by yz, dyz? This is your y-axis, this is z-axis. Yes or no? This is your dyz. Now I am not getting the ligand along the z direction. So these lobes, which are in between the axis of y and z, they will be affected slightly or not? May not be great, but there will be affection or not? Because there is an electron density in between y and z axis in the dyz. In the dxz also, we are removing ligands from the z direction. So if you are removing ligands from the z direction, the dxz, the dyz, their repulsion will be decreased or not? But when compared to dxy, if you take dxy, is there any affection in the dxy? Because along x direction also ligands are coming, along y direction also ligands are coming, and ligands are not in the z direction. So repulsion of dxy will be higher or not when compared to dyz, dzx? So T2g will now also split into two parts. What is the first part? dxy, which will be high in energy. Why? Because it will experience more repulsion when compared to dyz, dzx. Now the question is dx square minus y square is the highest. That's fine. dyz, dzx, they are lowest. That's fine. But among dz square and dxy, which is highest, which is lowest? dxy is higher, dz square is lower. So complete splitting happens like this. Write down all of you. This is your dx square minus y square. And after that dx square minus y square, you have dxy. After that, you have dz square. After that, you have dyz, dzx. So this is how the splitting in square planar complex. dx square minus y square will be the highest, then dxy, then dz square, then dyz, dzx. This will be the splitting in the square planar complex. This will be the splitting in octahedral complex. From the octahedral, we produce square planar by just removing the ligands from the z direction. That's it. Is everything clear, students?
Sir,
Yes, Nandana.
sir, like in NiCN4, it's only 4 ligands, right? So why don't we? Why isn't like tetrahedral complex formation happening? Like tetrahedral splitting?
Yeah, in NaCN4 we have only 4 ligands, so why can't it be tetrahedral splitting? That was a question, right?
Yes, sir.
So is it a complex tetrahedral complex?
No,
Forget
sir.
about splitting. Forget about octahedral splitting or square planar splitting or tetrahedral splitting. What is the shape of that complex? You figure out first.
It's a square planar.
If it is square planar complex, if the ligands are coming along in the square planar direction, how come the tetrahedral splitting happen? Are you getting this or not?
Oh, yes, sir. Yeah, yes, sir.
If the shape, you are only saying the shape is square planar, then how you can assign the tetrahedral splitting? The tetrahedral splitting is assigned only to tetrahedral complexes. You have to assign square planar splitting for square planar complexes. Okay?
Okay, sir. Yeah.
Okay. Fine, students. So in the tetrahedral splitting, what happens? Now we have seen octahedral, square planar, tetrahedral splitting. What is going to happen? In the tetrahedral splitting, what will happen? How the tetrahedral is formed now? Just imagine. Like we have a metal ion here at the origin. If ligands are coming along plus x minus x plus y minus y plus z minus z, do we have a tetrahedron formation? We do not have a tetrahedron formation, right? If the ligands are coming along the axis, that is not at all a tetrahedral complex. So ligands are not now coming along the axis, they are coming in between the axis. Like if one ligand is coming like this, like tetrahedral, if one bond is like this, the 3 other bonds should be like this. Yes or no?
Yes, sir.
So tetrahedral means, so this is what tetrahedral looks like. Okay. So you can see my wrist has one centimeter atom. This is one ligand. This other ligand. Yes or no? This pen. If pen is to one bond is like this, other bond is like this, other bond is like this. That is a tetrahedral. So in the case of tetrahedral complexes, you are not having ligands approaching along the axis. Write down that point. In case of tetrahedral complexes, ligands are, yes, Farhan, any doubts? Yeah, in case of tetrahedral complexes, ligands are approaching the metal ion in between the axis. and not along the axis. Yeah, no need to be sorry, Farhan. Okay, fine. So in case of simple logic octahedral complexes, ligands are approaching along the axis plus x minus x plus y minus y plus z minus z. Square pillar complexes, ligands are approaching along plus x minus x plus y minus y only, no ligands in the z direction. Tetrahedral complexes, ligands are not approaching along the axis, they are approaching in between the axis. If the ligands are approaching in between the axis, how the splitting will occur? Can I say those d orbitals whose lobes are in between the axis, they will have high energy? Those d orbitals whose lobes are in between the axis, they will be having higher energy when compared to those d orbitals whose lobes are along the axis. So we know again two sets. But in the tetrahedral splitting, we call them as, instead of T2G and EG, we call as T2 and E sets. In the E set, we have dx square minus y square dz square. In the T2, we have dxy, dyz, dzx. Understood now, students? Instead of T2G and EG, we call them as T2 and E in case of tetrahedral splitting. Tetrahedral splitting. So first point is, all the metal ions are considered as positive point charges. All the anionic ligands, they are considered as negative point charges. All the neutral ligands, they were considered as negatively charged dipoles. In the electric field of ligands, the 5 d orbitals of metal ion no longer have exactly same energy. So what is going to happen is, the d orbitals which are degenerate, they split into different energy levels or different sets. In the octahedral splitting, we have T2G down, EG above. In the tetrahedral splitting, we have E down, T2 above. In the square planar splitting, we have many splittings like dxy, dx square minus y square will be highest, then dxy, then dz square, then dyz and dzx. Okay. Now you have to understand how the electrons are going to be filled into these orbitals. Like from the valence bond theory, we have directly said that. If we have a strong field ligand, it will pair the inner electrons. But now, according to CFT, what I'll say, we have splitting happened in the presence of ligand. Let us consider an octahedral complex. Splitting happened. I have EG and T2G. Now I have to arrange electrons. How the electrons can be arranged? First electron I have to place in the EG or T2G. First electron. If I have only one electron in the complex D1, that has to be placed obviously in the T2G, no more choice. Second electron again has to go into T2G, but not into the same d orbital. Hund's rule followed. Third electron again into the T2G, Hund's rule followed. Fourth electron, whenever I am placing, that fourth electron I have to place in T2G or EG. That is decided by ligand. If you have a strong field ligand, what happens to the fourth electron?
It will pair.
Strong field ligand means the difference between T2G and EG is high. So the fourth electron is going to be paired up. If we have a weak field ligand, the fourth electron goes into the EG. So like that, we have to write the electronic configuration from D1 to D10 systems. Right, students? Today I have just explained the splitting in octahedral, tetrahedral, square planar. Tomorrow we will be looking at slides and all the animation points. Okay. So the animation is important to visualize, like to understand how the splitting is happening and why. But you have to understand without animation only. You have to visualize the whole scenario, because animations are not available in the exam, right? So we have to understand how the splitting happens, why it happens. We will be solving a lot more examples in the next class. Fine. Thank you all, everyone. Bye-bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.